Thank you.
Yep. Yep, I'm definitely recording now. So 2 million light years away. A light year is the year that is the distance that light can travel in 1 year. This thing is actually, if you know where to look in the sky, you can see this without a telescope. It won't look this spectacular. It will look like a little fuzzy patch in the sky. But you can look, if you know where to look for it in the constellation Andromeda, you can actually see on a dark night without a lot of lights around, a little fuzzy patch in the sky. Those particles of light that are hitting your eye from this galaxy left it 2 million years ago. It's kind of hard to wrap your brain around, but the Earth was a much different place when those light particles left the Andromeda galaxy that have traveled 2 million light years and are entering your eyeball when you go out on a dark night and look at this thing, even without a telescope. But if you want a pair of binoculars, this thing will look pretty spectacular through a good pair of binoculars. Yeah, what was happening on the Earth 2 million years ago? I don't know.
The same size as Milky Way?
It's a little bit bigger. We think it's about 50% more massive than the Milky Way, but on the same order of magnitude size as the Milky Way.
So if we wanted to get a picture of the Milky Way, we'd have to fly roughly 2 million light years.
Yeah, you wouldn't have to go quite that far, but sure, if you want to get this image of the Milky Way, you'd have to go to, the Milky Way looking back at us sees a pretty similar picture, maybe a little bit smaller. That's right. So it's a good question. What was happening on the Earth 2 million years ago? I don't even know. There were no humans around. Dinosaurs, you have to go back 92 million miles, 2 million years, I think. So it's not like dinosaurs are roaming around, but there are certainly no people.
I think it's the birth of mankind is 2 million years ago.
Is that right? So things that you would call people-like things are 2 million years ago? That's possible.
Yeah, they started evolving back then.
So the interesting thing is we're not seeing Andromeda as it is now. We're seeing it as it was 2 million years ago because the light has taken us that long to get to us. If somebody with a really, really super advanced, powerful telescope in Andromeda were looking back at the Earth, they would see the Earth as it was 2 million years ago, and they would have no idea that we're being able to build telescopes that can look back at them now. So this is one of the weird things about astronomy. If you want to study the past in astronomy, it's actually really easy to do, right? If you're an anthropologist and you want to study what an ancient civilization looked like, what do you have to do? You have to go and find some archaeological site. You have to dig up some ancient shards of pottery, and from that pottery, guess about what kinds of things they ate and what kinds of lives they lived and what kind of rituals and ceremonies they had and what gods they believed in. You have to make educated guesses based on the things that they built that have survived from those ancient civilization times today. If we want to know what galaxy, now if we don't want to know what the Milky Way was like a long time ago, we have a problem. But if we want to know what galaxies in general were like in the past, it's easy. You can actually still see them. The Andromeda galaxy is our neighbor, right? 2 million years on a cosmic scale is pretty short. It's pretty short distance, actually. We don't think galaxies evolve much on 2 million year time scales, but the universe is 13 to 14 billion years old. And so if we can look back 1 billion light years away, or 5 billion light years away, or 10 billion light years away, we can see whether galaxies have evolved and how those galaxies have evolved and whether galaxies look different 13 billion years ago than they do today. And it turns out they do look substantially different today than they did 14 billion years ago. Where am I going with this? Okay, so this is one of the coolest, another one of the coolest images that's been taken in astronomy. This is, I actually set this up a couple of years ago. I'm 90% sure this is the Hubble Ultra Deep Field. So the story of this picture is, the Hubble Space Telescope was launched in 1992 now, actually. It's almost a 30-year-old telescope. And very early on in its history, it was a very oversubscribed telescope. So in other words, astronomers, it was the best telescope that had ever been built, and you could do things with it that had never been done before. And so lots of people wanted time on this telescope. And in fact, it had an oversubscription rate at the beginning of 10 to 1, meaning that for every 10 proposals for time on the Hubble Space Telescope that were written and submitted, one of them was accepted. And these are, these aren't Joe Schmoes. These are the best astronomers in the world, proposing extremely exciting and original research on the world's best instrument at the time. Anyway, I'm telling you that because to know that the director of the telescope in its first couple of years had some what they call director's discretionary time, where he, as a reward for being the director of the telescope, had about a day's worth of time to spend on whatever he wanted to do as a reward for being the director of the telescope. Very valuable time. And he decided that the thing that he wanted to spend his entire day's worth of observations doing was to look at the most boring patch of the sky that he could possibly find. Like, seriously, he found a region of the sky, I think it was in the Ursa Major constellation, that had almost no known stars in it. It was outside the plane of the galaxy. It had no known real galaxies in it. And he just sat for the entire day and gathered photons from the Hubble Space Telescope on basically a blank patch of the sky. And this isn't that image.
Solid angle or the horizontal angle?
Sorry?
Do you know the solid angle or the linear angle?
It's small. It's probably I want to say 3 or 4 or 5 arc minutes on a side. An arc minute is a 60th of a degree, probably, is what we're looking at here. So yeah, this is a couple of degrees across, right? This is a very wide field image. This is a, you know, on this scale, it's probably like, you know, the distance between these stars here or something, right? It's a very much smaller patch of the sky. Does that answer the question, Pogo?
Yes.
Okay, great. And the thing was just full of galaxies. It was full of galaxies. It was so successful that they went back several years later and did the Hubble Ultra Deep Field, in which they took, I think, 10 days worth of exposure times in various filters, split up between various filters, on an even more boring patch of the sky that they could find. And this is that image. This is the Hubble Ultra Deep Field. It is still one of the deepest images of the universe that has ever been taken. And almost every single thing that you see in this image is a galaxy. With the possible exception, I think, of this thing as a foreground star, and this thing as a foreground star, and maybe this guy. Everything else is a galaxy. And the amazing thing is, there are galaxies that span from relatively nearby to galaxies that are at the very edge of our visible universe. And so this is a snapshot of, it's not even a snapshot, it is a look back not only through space, but back in time. And you can do a survey and a study of galactic evolution just by looking at galaxies at different distances from us. So you can see this thing, a beautiful spiral galaxy here. This is what normal galaxies look like in this part of the universe today, although not all of them. This is a nice spiral galaxy. This is another galaxy that's not a spiral. It's called an elliptical galaxy. And you can see some interesting differences between the spiral galaxy and the elliptical galaxy. One is, so here's another elliptical galaxy, here's another elliptical galaxy, here's another elliptical galaxy. You can see, obviously, these elliptical galaxies don't have the spiral structure. Do you notice anything else that's different between the spiral galaxy and the elliptical galaxy?
The color.
Color, exactly. The spiral galaxy is blue-ish, and the elliptical galaxy is kind of red-ish. That gives us important clues about what's going on in the galaxy. Because where does the blue light come from? The blue light comes from the very brightest, hottest, most massive stars in a galaxy. Those brightest stars lead very, very short lives. They explode as supernovae, you know, within just, I don't know, a few million years or so, right? Almost nothing. So the fact that this galaxy looks kind of blue, and this galaxy looks kind of blue, and this galaxy looks kind of blue compared to these guys, says that there are young, hot, massive stars in them. It says that there's star formation currently happening in these stars. And there are young stars in them that would make them look blue. These guys do not have present star formation going on in them. And you can tell just by looking at the color, this is an older much older population. There are no stars that are as young as 10 million years, say, or it would look much bluer. So you can just, looking at the color, kind of guess some aspects of the history of the galactic evolution of these individual galaxies. But that's not what's the most interesting, right? We see elliptical galaxies. In fact, you look back to the previous, this is a beautiful spiral galaxy, but this is an elliptical galaxy, and this is an elliptical galaxy. It doesn't look like they're substantially redder, probably because of whatever filters they've used to take these images, but they should be. This should be a substantially redder galaxy than this. And you can kind of see that it's more blue in some of these outer bands in Andromeda than it is in these two galaxies.
In the Andromeda picture, all the background dots, are they stars or galaxies?
Almost all of those are foreground stars.
Okay.
Which is because we're looking at such a wide view, we get a lot of. Whereas this is such a narrow view, we just don't have that many of them. Yep. So yeah, you're sort of looking through a fog of nearby stars to get to that very, very distant object. But in this galaxy, in this picture, there are nearby galaxies, and I would say all of these big ones probably are, and there are intermediate sized galaxies, and there are galaxies that we know are 10 billion light years away, 9 billion light years away, 12 billion light years away, that we're seeing as they were 10 to 9 to 12 billion years ago, right? We're seeing them as they were when the universe was only 1 to 3 to 4 billion years old. And so the universe was much different then. And we can track how the universe has evolved and how these galaxies evolved just by looking at this one picture. It's pretty amazing. Okay, so how can we determine, let me know how we know that Andromeda galaxy is 2 million light years away? How can we possibly determine that? We don't have ruler sticks, meter sticks that extend that far, sadly. So how do we know? How can we measure the distances to any of these galaxies, for that matter?
Can you use
By
the Doppler effect?
The Doppler effect, by the wavelength. So interesting. How are we going to use the Doppler? The Doppler effect, let me remind people who might not be familiar with it, the Doppler effect is it's the same effect why when you have like a race car going by, it changes in pitch as it passes you, right? So as it's moving towards you, those waves the sound waves all get compressed and you hear a higher pitch. And then as it's going away from you, those wavelengths, the wavelengths of the wave all get stretched out. And so the pitch goes down and you hear a lower pitch as the car is moving towards you as opposed to it's moving away from you. That's the Doppler effect. So how are we going to use the Doppler effect to get distance? We can use it to get velocity, right? How fast that object is moving towards us is going to determine how scrunched those waves get, and is going to determine what the frequencies are. You could imagine doing that for light, which I presume you're doing for these. So we can determine the velocities of these things with the Doppler shift, but how is that going to give us a distance? In fact, we sort of need to know the distances a priori. Well, it actually is exactly right how we do this one, but in general, it's for Andromeda, because Andromeda is actually an exception to the rule that we're about to talk about. Andromeda is moving towards us. Andromeda is the gravitational force between the Andromeda galaxy and the Milky Way galaxy are actually pulling them towards each other. So we're actually on a collision course with the Andromeda galaxy. In another 5 billion years or so, our two galaxies will merge and coalesce and probably form some massive bigger galaxy. So how are we going to determine the distance to Andromeda? Anyone know? It's not easy. In fact, we did not know the distance of this galaxy until about 100 years ago.
Parallax?
In fact, what's that?
Can you do Andromeda with parallax?
No, it's way too far to do with parallax. So parallax is a good one, right? So the Earth is going around the sun. And so if you have a nearby star, the Earth is actually in two different distinct positions 6 months apart. And if nearby stars are near enough, then you know, move your head back and forth, you'll actually see nearby things move with respect to far away things. So you can use that to get distances to nearby things. And we've gotten good enough that we can, only in the past year or two, that we can do that out to things kind of near the center even of our own galaxy. It was a satellite that was measuring these things, I don't know, 15 years ago that came out. And even then, we're at a fairly small, you know, if we're out here in the outer part of our galaxy, as of before 2 years ago, the best we could do was be about a circle about this around us where we could do parallax distances. And before 15 years ago, it was much smaller than that. It was a circle about that big around us where we could actually get parallaxes. So yes, that works for very nearby things, and that's important, but it's not going to get us Andromeda. And go back to my story, there was a great debate in 1917 between two prominent astronomers about what this thing was. And the two camps were, one, this is what we think it is today. It's its own galaxy. It's like the Milky Way, only it's much further away, and it's as big as the Milky Way is, and it's its own galaxy. That was the island universes theory. The other theory, held by prominent professional astronomers at the time, was that these were objects the Milky Way was the universe, and that these things were much smaller than the Milky Way and much closer to us, therefore, and within our own galaxy. And the only and nobody really won that debate because nobody had ever figured out exactly how far away these things are, right? Distance is very important in astronomy. Is this a nearby thing that isn't very big at all? Or is this thing really far away and really ginormous, right? Without knowing the distance, there's no way to be able to tell the difference between those two things.
Could you follow the time it takes for like something to burn out in space, like a star?
Right. So let's think about that. We know that there are stars. Well, first of all, the time scales are too long, right? We live for maybe 80 years, and stars, even the really fast ones, really massive ones, live for hundreds of thousands of years, right? So there's a time scale problem there. You can't see a star go from its birth, meaning collapse from a cloud of gas, to supernova. You can't watch that whole thing over a single lifetime. But even if we could, how does that help us? Right? It's just going to be delayed. All of it's going to be delayed by 2 million years, or by 1 million years, or by 20,000 years, depending on how far away this thing is, right? So watching it go through the phases, you know, it's not going to seem to move any faster or slower if it's further away. It's just going to be delayed by that amount. But the beginning and the end is going to be delayed. That doesn't really help us. It's a good guess, though. It's a tricky problem. The answer is you need to use some sort of standard candle. What do you mean by that? I mean, something whose brightness, whose luminosity, whose intrinsic brightness you know, right? So let's say a supernova does go off in Andromeda Galaxy, right? It's going to be some really bright thing, might be brighter than the combined light of the galaxy itself. If we know it's a particular supernova, say, and we know that particular kind of supernova always gives off a certain amount of light, meaning energy per second per square meter, just energy per second, and we can measure the brightness of that thing, then we can use how bright it should appear versus how bright it does appear to figure out how far away it is. And so this was done with a class, it wasn't a supernova, because, well, you have to wait a long time for a supernova to go off. A galaxy this size has a supernova go off in it about once a century. But there are other bright stars in Andromeda Galaxy. And what this guy did, this is Edwin Hubble smoking his pipe at the Mount Wilson Observatory. And he was taking basically pictures of the Andromeda Galaxy, and way zoomed in pictures of the Andromeda Galaxy. So we will be looking at maybe this particular section of the Andromeda Galaxy, or this particular section of the Andromeda Galaxy. And he noticed that there were some stars. If he took the same image night after night after night, there were some stars that were variable stars. They were varying in brightness. They were getting brighter and then fainter and then brighter and then fainter. And he realized that there were some similar objects that he knew of that varied at exactly the same way and exactly the same, not the same rate, but there had been studies on these objects earlier that had related how luminous they are, meaning how much energy they actually emit as per time, to the period of that rise and fall. And what these basically are, they're called Cepheid variables. They're physically pulsating stars. So they get physically larger and then they get physically smaller, and they get physically larger and they get physically smaller due to some weird instability, right? There's some weird instability that changes sign as it gets bigger and smaller. And so these things physically pulsate. And the bigger they are, the more luminous they are, the longer it takes to go through that. The more mass there is to move, the longer it takes to go through that cycle. And so the how long it takes to go through that cycle, which is really easy to measure, is related to how big it is, which is related to how luminous it is. You can use these things as standard candles. If you can find one of these variables in Andromeda Galaxy and watch it go through its up and down cycle of brightness and measure the period, you know the luminosity. And if you know the luminosity and the brightness, you can work backwards to get the distance. And Edwin Hubble did that, and he found that the Andromeda Galaxy is, and he was the one who solved the whole problem. He realized that Andromeda Galaxy is about 2 million light years away, which is way bigger than we had for the Milky Way. And so this thing must be its own universe, its own galaxy further away. Anyway, that's weird. And we know that the Andromeda Galaxy is moving towards us. When we look at other galaxies in the universe, though, almost every single galaxy in the universe is moving away from us. Again, we know this by the Doppler shift. So here is a cartoon showing two galaxies, right? This is so what is a spectrum of a galaxy? It's basically the combined spectrum of all the stars in that galaxy. And what is a spectrum? Well, again, it's how bright the thing is as a function of wavelength. This is the wavelength of light. So again, light is a wave. It comes, you can define its wavelengths. In fact, this is color. 400 is about the limit of the visible part of the spectrum. These are very blue photons. 500 is kind of green. If you go off into the 600s and 700s, you're in very red photons. So this is the end of the visible part of the spectrum right here. But there are features, right? So we know that galaxies and stars that make up the galaxies have these absorption features that happen at very specific points, right? And so when we look at a distant galaxy, we notice that those features, which appear at, let's say, in the 370s or the 360s in this galaxy, we look at a distant galaxy and they appear redshifted, right? They appear at longer wavelengths. This is an example of a 5% redshift. So this is not unusual. We know that this happens. In fact, when we look at stars, some of them are redshifted and some of them are blue shifted, just happen to be how they're moving towards us or away from us along our line of sight. When we look at galaxies, though, every single one of them is redshifted, aside from a very small number of local galaxies that are blue shifted. Every single other galaxy in the universe is redshifted. What does that mean? It means its photons have been shifted towards longer wavelengths, which means that in the sound wave analogy, those objects are moving away from us, right? When they move away from us, all those wavelengths get stretched out, and we see that as a redshift. Why do we call it redshift? Well, the red end of the spectrum is on the long wavelength end, and these things have been moved towards the long wavelength end of the spectrum. So we call that a redshift. So that's weird, right? So Edwin Hubble, again, he determined the distance of the Andromeda Galaxy, and so he pointed at lots of other galaxies, and he started measuring. He started finding Cepheid variables in those galaxies, and he's measuring the distances to galaxies, and he's taking spectra of them, and he's finding the redshift of these galaxies, and he noticed something pretty amazing. Oh, here's examples of some other redshifts, and some of these redshifts are amazingly big, right? Here's a galaxy in the Virgo cluster, that is moving away from us at 1,200 kilometers per second, right? That's really fast. 1,200 kilometer, more than a kilometer every second. And these are two, you can see the two prominent lines, this H and K lines, and this particular wavelength. Here is a galaxy in a more distant galaxy cluster. And we know that this is further away because of Cepheid variables, but also because it's smaller, right? In fact, we expect all these galaxies are about the same physical size. And so the only reason why this one looks smaller than Virgo is because it's further away. And look, those two H and K lines have been shifted from this point all the way out there. This guy is moving away from us at 15,000 kilometers per second. An entire galaxy moving away from us at 15,000 kilometers per second. Here's one in Corona Borealis, 22,000 kilometers per second. The Bootes cluster, everybody's favorite cluster, not the void, but the cluster, 39,000 kilometers per second. The Hydra cluster, 61,000 kilometers per second. That's really fast. Do we know how fast the speed of light is? You can look it up if you want. Somebody type it in the
3 times
the
10 to
chat.
the 8 meters per second.
3 times 10 to the 8 meters per second. Exactly right. So what is it in kilometers per second?
3 times 10 to the 6th.
Close.
3 times 10 to the 5th, right?
10 to the 5th. That's right. It's a factor of 1,000. 10 to the 3 different. 3 times 10 to the 5th. All right, great. In 1,000. 3 times, so 10 to the 5 would be 100,000, right? So 3 times 10 to the 5 is 300,000 kilometers per second, right? This galaxy is moving away from us at 60,000 kilometers per second. That's 20% the speed of light. These are not small velocities. These galaxies are cooking. How do you get an entire galaxy to be moving at a velocity of 20% the speed of light? It's a good question. So this is the guy who was doing all this stuff, Edwin Hubble. He was, so this is a picture of the Mount Wilson telescope, which is actually on a mountain that overlooks the city of Los Angeles. And he was doing these observations in the 20s mostly. He made all of his observations sort of between 1920 and 1930. And you can see this is not really how it's done today. Back in the day, if you want to take an image of a actually this is probably a prime focus telescope. So how do telescopes work? There's a mirror down here, and modern telescopes, there'd be a secondary mirror up here that redirected the light probably back down through a hole in the primary mirror where your imager would be down here somewhere. I'm guessing this is a prime imaging instrument, which means that instead of, so the light does come down here, it hits the primary mirror and gets focused back up here, but whatever instrument you're using, and back then it was just glass plates, you'd put the glass plate in a little holder, and you would let it develop, right? And then you'd put the glass, you take it out and put it in a glass, in a protective case, and then you take it down to your dark room and develop it, right? And then you get a negative, and you could use that negative to make a positive image if you wanted to. Obviously, all this stuff is done electronically now. We have nice big CCD cameras that can take electronic images for us. But back in the day, you probably had to ride around in this telescope and change out the plates periodically as you were going through the night. It was a big deal back then. You can see like easy chairs and desks in the dome itself. This doesn't really happen anymore. There's actually a funny story of an astronomer who was smoking his pipe in the dome and discovered some very unusual absorption lines in a star that had never been observed before. And he published this paper, and they realized after the fact that it was probably the pipe smoke getting in front of the lens of the mirror of the telescope that was giving those absorption lines, and not in the star itself. So that's a, you know, if you're going to smoke your pipe, don't do it in the observatory while you're taking your data. Just a word of warning. Anyway, so again, Hubble was the guy who discovered Cepheid variables in Andromeda and determined the distance and settled that debate. He went on and measured distances to lots of other galaxies and measured radial velocities of other galaxies. And he noticed something rather peculiar and rather unusual and rather amazing. And that is, not only is it that all these galaxies are moving away from us, meaning they have a positive radial velocity, but the further away a galaxy is from us, the faster that galaxy is moving away from us. It's a pretty amazing thing, right? So here is velocity. Then this isn't Hubble's data. Hubble's data was all down here, and it's pretty amazing he was able to even determine this because it was very noisy. But he did, and it turned out to be right. So again, this is distance, how far a galaxy is away from us. This is its radial velocity, how fast it's moving away from us. A negative radial velocity will be moving towards us. A positive radial velocity is moving away from us. You can see all of these galaxies are moving away from us. And there's this very cool linear trend where the further away it is, the faster it's moving away from us. It's hard to overemphasize how weird this is, right? When we make a similar plot, let's say of stars in our nearby region, it looks nothing like this, right? It's a scatter plot, right? Some of them are moving towards us, some of them are moving away from us, and there's no relationship at all with distance, right? It's just a weird scatter plot. Look at how tight this fit is. And this is actually not as good as the data we have now. The data we have now is a much tighter fit to this particular graph. So it's very weird. We can, of course, write an equation to characterize this weirdness. Once you have a linear relationship like this, you can draw a straight line through it, and you can call it a law, and we do. It's a Hubble law. So how would we do this? Well, y equals mx plus b. Our y variable is velocity. Our x variable is distance. And b, it turns out, is 0 because this happens to go through the origin, right? So all you really need is y equals mx. Velocity equals the slope times the distance. And that's what the Hubble law is. Velocity equals the slope of that line times the distance to that galaxy. And we happen to have a name for the slope of this line, and we call the slope of this line the Hubble constant, h naught. And it's got this weird unit, kilometers per second per megaparsec, which is a really weird unit of distance. A really weird unit at all, right? Anybody know what a parsec is? What unit is that? Is that a time? Is that a energy? Is that a velocity? Is that a
Something about the Kessel run, as I recall. Steve, do you remember?
Definitely got some Kessel runs in there, which was why people are confused about what this unit is. If you don't get that joke, it's a Star Wars reference. There's a famous scene, if you've ever seen episode 4, which is the original, where Han Solo is talking to Greedo. No, he's talking to Obi-Wan Kenobi and Luke about the Millennium Falcon, and he famously brags about its speed, saying that it made the Kessel run in less than 12 parsecs. But that doesn't help you at all solve this problem, because that's a totally misuse of the word parsec, sadly. It is from Star Wars. Anyway, but they stole that term from astronomy. Astronomers didn't steal that term from Star Wars, actually. A parsec, it's about 3.25 light years. That's exactly right. It's a unit of distance. In fact, it comes from the parallax thing, right? So what is a parsec? A parsec is a distance that a star will have if it has a parallax angle of exactly 1 arcsecond. So as the Earth is going around the sun, this star will appear to move in the opposite direction. And if that motion is exactly a parsec, then an arcsecond, then that star will have a distance of 1 parsec. It turns out it's 206.265 astronomical units, which is the distance between the Earth and the sun, because that's the number of arc seconds in a radian, which is a very convoluted thing to say. If I were on the board, I could show you all this. It doesn't really matter though. But parsec means literally parallax angle arc second. They just shortened all that into parsec, and it's a unit of distance. It happens to be about 3.26 light years, 3.5 light years. So It's a rather large unit of distance. It's more than a light year, but still the closest stars to us have distances of a little bit greater than 1 parsec besides the sun. So it's still not all that big on cosmic scales, and certainly not all that big on extragalactic scales. In any event, a megaparsec is a more usable distance for intergalactic distances. A megaparsec is just 1,000,000 parsecs. So it's a big distance that's suitable for measuring distances to distant galaxies. So we're going to measure velocities in kilometers per second because that's what we measure the speed of light in. We're going to measure distances in megaparsecs. So the slope of this line is going to have units of kilometers per second, units of rise over run per megaparsec, right? But this is weird because the kilometers is a unit of distance and megaparsecs is also a unit of distance. So this is really a unit of inverse time, because you could take this kilometers and cancel out with this megaparsecs. It just wouldn't give you a nice number like 72 anymore. Okay, so what am I at? I'm 7 minutes left. Good Lord, where has the time gone? So what are the implications of this? Why is this weird? What is going on? Well, you can use this for some very, very useful things. For instance, let's say you have a galaxy that's 200 megaparsecs away and it's moving away from us at a speed of, it looks like 1.4 times 10 to the 4, oops, kilometers per second. Right, so that's interesting. There's a galaxy that's moving away from us at a certain speed, and you know how fast it's moving away from us. If you rewind the clock, you can imagine calculating how long ago that galaxy is where we are now. Right? You've got how far it is away now. This is an analyte 1 problem. You've got how far it's moving. H naught's kind of in hertz, that's right. You've got how far it's moving, fast it's moving, and how far away it is. It's not a hard velocity equals distance divided by time to figure out how long ago that thing is where we are now. And you'd get a number. That's interesting. Okay, great. So you get a number for this galaxy at 200 megaparsecs away. What about this galaxy at 100 megaparsecs away? Right? We could do the same thing, right? It's half as far from us, but it's also moving away from us half as fast. So what are we going to get for the time where this galaxy was in the same place that we are now? It's going to be exactly the same. Here's one at 300 megaparsecs. It's 3 times further away, but it's moving away from us 3 times faster. This is weird. It implies that in the past, all of those galaxies are where we are now, and that happened at exactly the same time. This is why we think the universe began very hot and very dense, because it seems to be expanding now. This is an expansion of the universe thing, right? All those galaxies are where we were. We're where we are a certain amount of time in the past. And in fact, it's the inverse of the Hubble constant that tells you how long ago that was. And if you just make that simple calculation, you get a number that's about 13.5 billion years. It's a little more complicated than that, but there's 2 complications that kind of offset each other and give you almost exactly the same answer as you get for that same very simple thing. So that's really cool. One, that's why we think there was a Big Bang. The universe began very hot and dense because we see all these galaxies moving away from us now. If you rewind the clock, all those galaxies are where we are, were in the very distant past. So that's fun. So what is expanding? So this is an interesting thing. So people look at this kind of thing and say, hey, it must be therefore that we're the center of the universe, right? We look out, we're not moving, obviously. We look out in that direction, we see galaxies moving away from us. We look out, it doesn't matter what direction you point in. The galaxies are moving away from us, and the further away they are, the faster they're moving away from us. That's the Hubble law, right? So are we the center of the universe? How many think yes? I mean, I'm obviously the center of the universe. But maybe the Milky Way is too. Yay, Nick. Thanks for voting. I could open up a little vote here. I've never done that before, but we probably don't have time. What am I down to? 3 minutes. Great. Anybody else want to chime in? Thank you for the no. Okay, so I've given the yes. I've given the yes explanation. Anybody want to try to give the no explanation? How is it that we're not the center of the universe? It's got to be about the money. It's relative to what? Okay, so this is very hard to explain in words, but not all that hard to explain in diagrams. So let me try. Let me show you what I've got here. This is one of my favorite simple demos of all time. Let me change my video to this thing. That's not working. There we go. Are you seeing this now?
Yep.
Good.
Excellent. Okay. So what have I got here? I've got a part of the universe, right? A 2D part of the universe. I've got a green galaxy, I got a blue galaxy, I got a red galaxy, and an orange galaxy, right? So this is just a piece of transparency, nothing special. On the other, I've got another version of this too. I've got two versions of this, and between them, I have pressed the enlarge button on the copier by 10%. So one of these has been enlarged by 10%, and this is cool because I can overlay these on top of one another, and voila, I get the Hubble law, right? So we're here at the center of the universe in the galaxy, and we look out and we see that the further away we look in space, the farther these galaxies have moved in that 10%, right? This is the Hubble law. We've got it right here. All I had to do was press the expand 10% key on the copy machine, and we got there, right? So we're the center of the universe then, right? Wait, what if I do this from the perspective of the blue galaxy? Ready? The blue galaxy sees exactly the same thing. From the blue galaxy's perspective, it's standing still and everything else is expanding away from it. From the red galaxy's perspective, the red galaxy is standing still and all the other galaxies are expanding away from it. You can do this for any point on the chart, and everybody sees the Hubble law from wherever they happen to be. So the answer is there is not a center of the universe, and the Hubble law is actually seen by everybody all the time. So somebody looking at us from 12 billion light years away will see us as we were 12 billion years ago, but we won't have been here. Cool. Any questions? The universe is expanded, can't pinpoint. Right. There is no center of the universe. The universe is just expanding uniformly in all directions everywhere. It's still possible to have a finite universe, interestingly, but there is no center. We think the universe is fairly homogeneous, meaning it looks about the same everywhere, and either it's infinite in extent, in which case there's no center, or, and this is the weird thing, it could be curved, could be curved in some weird three-dimensional way that's impossible to wrap our brains around, right? If you could imagine a two-dimensional universe that's curved in this way, you could imagine it being curved around in a sphere, right? A two-dimensional universe that's curved around in a sphere would have a finite area, but no center to the surface of that sphere, right? A two-dimensional being on the surface of that sphere could walk in a single line in a single direction and eventually come back to where they started from. It's possible that we live in a universe that is curved in three-dimensional sense, so we could take a spaceship, go off forever in one direction, and eventually come back to where we started from. Or it could be infinite and just extend everywhere in both directions. But either way, there is no center physically of the universe itself. So that's the bottom line. And I am completely out of time. So if you have questions, you can either send me emails or you can stop by and visit me sometime. I'm an ISC 217. It was nice to see everyone. Thank you for your participation and thank you for your questions. We'll do it again on Zoom next week with Dr. Pogo and Spider Silk. Enjoy the rest of your Wednesday, everyone.
Thank you.
Thanks, Aaron.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thanks.
Hey, Aaron, I have a question for you.
Yeah, go ahead.
So, I've seen that before and I've seen these explanations many times, but where's the experimental evidence that this is actually what's happening? I mean, I don't see it experimentally. We can't sit on another galaxy and show that, it's stretching from that point in space. We can only sit here. And so how do we use this argument that it's not just a bunch of objects moving away from us to the argument that space is actually being stretched?
If it were an explosion, say, instead of well, I mean, let's see. It's the cosmic microwave background, really, right? So you go far enough away and eventually you'll come to, we can actually measure what the universal standard of reference frame of rest is. And we're pretty close to it. We're within a couple hundred kilometers per second of the universal standard rest frame. And that's set by the cosmic microwave background radiation, right? So the fact that we can look out and see the cosmic microwave background at that rest velocity, I think rules out an explosion. I have to think about that kind of carefully. But even so, I mean, there are now galaxies at the edge of the visible universe that are moving away from us at near the speed of light, right? How does that happen when, so I mean, that cosmic microwave background itself is redshifted by, way more than any galaxy we've seen, right? But how do we know it's at rest? Well, we can measure it in that direction, we can measure it in that direction, it's almost exactly the same redshift. And that direction, it's almost exactly the same redshift in any direction we point, right? Which means and we can measure it, it's about 200 kilometers per second that we're moving with respect to that is the standard of rest, right? If we were at rest, if it were the same in all directions, we would be at the universal standard of rest. And a galaxy at the edge of our visible universe kind of must also see that, right? That the background radiation is also at rest relative to that galaxy. And so there's no other real way, I think, to even conceptualize it other than space itself expanding rather than galaxies moving through space.
Okay, I have to think about it. I'm not quite sure I totally get that. But yeah, I guess there's the other issue that why would these things be faster and faster as you move outwards for the explosion model, the classical explosion model, I'll call it.
Well, I mean,
that's a strange,
right.
Very strange thing in its own right.
You could imagine, well, if you start with a bunch of marbles all in the same place,
yeah,
right, and you scatter them, that's what exactly you're going to see. It's not going to be different than that.
Yeah, they're not
You'll get
speeding up. They just started faster and they're still faster.
That's right. But that's what this could be. I didn't say anything about speeding up or slowing down.
I'm just clarifying Steve's question. I agree with you.
Yep.
Yeah.
Yep.
So you're just simply.
So I think you would see the Hubble law in that case.
Right, because it's basically a bunch of race cars at the start,
right,
and they all have different speeds.
Exactly.
So some get out and ahead.
Exactly.
They're the fastest ones, so they're the farthest away.
Right.
Yeah, and so I guess that's where I'm kind of confounded by the
experimental
evidence of expanded universe.
General relativity doesn't work with that model either.
Right.
In order to explain the shape, the universe's existence at all, I think it has to be pretty homogeneous everywhere, meaning throughout. If it's not, then at least the equations we've used to describe the universe don't really work. And I think there's some real problems trying to come up with some that would in a model like that. Because you know, the universe is curved in a very specific way that is dependent on the mass in it. And if you start with a universe where all the mass is in a single place and it's empty everywhere else, the geometry of the universe is going to be very, very weird. And I don't think it even works to have a universe that way from a GR perspective, but I'm no expert at that.
That's a good point. Yeah, I do get that. I mean, if it's not the expansion of space and it's the expansion of material in a fixed space or in an infinite space, you get two very different results.
It's a two very different universes.
Yeah,
That's right.
Yeah, I guess that's a clearer way for me to see it. Boy, that's still, you know, every time I hear this and I think about it, it's just still the bizarrest thing.
It's mind blowing. That's the whole point.
It totally is. It really is. You know, no matter how many times I've heard this, you know, this discussion, I'm still just awed by it. You know, it's pretty cool. Well, thanks a lot. That was fun.
You're welcome.
A lot of fun. Okay.
Yeah,
I
looking forward to you guys next couple weeks.
Okay.
I looked up some pictures of the ultra deep field while you were talking. It's considerably better than the picture you were showing. You know.
Yeah, it is.
Higher res and more.
It is.
Galaxies.
That was even a small portion of the deep field.
Yeah.
I should just throw the whole. You're right. I should just throw.
I was surprised to find. Oh, it's even more than that.
It's even better than I showed. Yeah. Why am I holding out on you guys? Good question.
Exactly.
I should definitely not hold out on you guys. You deserve the best.
Hey, did I tell you some kid, I don't know, emailed me last week and asked me, Steve, you'd be interested in this too, asked me to prove to him, actually he didn't use the word prove, that people landed on the moon. He's like, there's no way we landed on the moon. Given the pace of technology back then, it would not have been possible. It's all been fake.
You don't want to go down that rabbit hole.
Was it a college student or some kid?
He said he was friends with some physics majors, and the physics majors tried to convince him and failed. And so they told him to write to me, like, whatever. And apparently I was fairly persuasive, though. I don't know what I said. First, you know, he said, I don't believe the video evidence, and I don't believe the transcripts. And I'm like, well, what do you believe in? Do you believe that Abraham Lincoln lived? There's no video for that. And transcripts, if they're all fake, then you don't believe that. Do you believe the terrorists blew up the two towers? Why? Because the videos, no, it's all fake. If you believe anything from history, then you have to admit video evidence or transcripts. And so I did that, but then mostly the thing that seemed to have pushed him over the edge was the existence of the lunar reflector module.
Yeah, that's one. But the other evidence now is there's a lunar mapping satellite that's been orbiting the moon for some time now, and they actually have images of where they landed. Well, that's pretty good to me.
You can't see the flag, but you can see the modules.
Yeah, you can't see the footprints, but you can see, you know, different parts of the landing site.
Yeah.
So unless they're faking that too, but I mean, that's just getting ridiculous, you know, I mean.
Yeah, I mean, honestly, the government is not competent enough to be able to fake something that big for this long. I mean,
it's good.
You're giving the government way too much credit. And
that's right. Yeah.
That's for sure.
Too many people would have had to have been in on that fake.
Yeah, it's just.
It never would have worked.
Yeah, absolutely. And you know, even, you know, another proof of that is that, you know, the Shadow Mercury project, right, which was a super secret project with a whole set of Mercury astronauts that no one knew about. Even that was unearthed. I mean, you know, and they were really, really trying to keep that secret, and they couldn't do it. So no way they would keep Apollo secret.
No way.
Yeah.
No way.
So anyway, okay, thanks a lot. That was a
all right, gentlemen. Yep. See you next week.
Aaron, procedurally, do you think you prefer the type questions or the oral questions?
I certainly preferred. It wasn't that big a deal. I didn't mind the I thought it would get weird with people interrupting and chiming in, but it was fine. It wasn't. There aren't that many of them, so it worked.
I'm just thinking about next week is all.
But I was fine with the chat too. I had it up. I could see what was going on. I could choose to ignore questions that I didn't want to address.
Nice.
I could choose, and I could circle back to them too. So it was kind of nice to have them in the chat actually.
Yeah, those questions about, is there really milk in the Milky Way?
Do you know why it's called that, Steve?
Let me see. Milky Way.
Because it looked like somebody spilled milk across the sky.
It kind of looks like a milky
That's what I would have guessed too. Yeah. I mean, because we're in the plane of it, so
In
Looks
fact,
like a
the word
strip of-
galaxy has the word lactate right built into it. Galaxy
Right.
is Latin for milk.
Really?
Yep.
Yep.
So it's kind of redundant.
It's
The
true.
Milky Way galaxy is, yeah.
It's
Yeah.
the Milky Way. It's the Milky
It's
Milky.
the only one that looks milky to us, though, you know.
Yeah, yeah, I guess so. Hey, that's interesting. Wow, what I'm learning from saying this. It looks like Carly's with us. Carly, you here or you just left your computer on? Hello, Carly?
You just fell asleep.
Yeah, I guess.
Carly.
Carly, are you there? Kind of
Hey,
embarrassed.
Aaron, I did have one student who missed, and if I can, I'd like them to watch the same video if you get that set up someday.
I will upload it to YouTube and send you a link.
Not a hurry.
Thanks a lot,
Bye.
guys. Tip.